Okay, so now we'll start the chapter capacitors and inductors, chapter 5. It has a small chapter. Only we discuss about the capacitors and inductors, how they are constructed and how they are behave when we give the DC supply, DC power supply. So we studied about capacitors. We will study about series and parallel combination of capacitors, how they can be calculated. Same thing for inductors. Same series and parallel inductors also we'll study inshallah. So what is a capacitor? First one. Okay, in this chapter, we shall introduce new and important passive linear circuit elements, the capacitor and inductor. So, unlike the resistors, so what we studied till now is only resistor, which is a passive element, which dissipates energy, means it will waste the energy. It will give the energy into the atmosphere, dissipates the energy. Capacitors and inductors do not dissipate. They will not dissipate or waste the energy. They will store the energy. Capacitors is static energy and inductors magnetic energy. Different types will be there and based upon the current and voltage. So you have to just note down capacitors and inductors will not dissipate energy, but it will store the energy. Opposite resistor. Resistor always dissipate the energy because it has a property of opposing the electrons. When the property of electrons opposition is taking place, some energy will be waste. Energy will be dissipated, given in terms of IR radiation, in terms of heat. So like this. But capacitors and inductors will store the energy. For this reason, capacitors and inductors are called storage elements. The name of the capacitor and inductors are called storage element. We begin by introducing capacitors and describing how to combine them in series and parallel also. So later we do the same for inductors. First we'll study the capacitors, then we'll go for the inductors. So a capacitor is a passive element designed to store energy in its electric field. Remember, capacitor means based upon voltage, electric field. Inductor means based upon current, magnetic field. These two terms should be remembered. Electric field with the capacitor, and capacitor is a passive element. Capacitors are used extensively in electronics, communications, computers, and power systems. See, they have very wide range. If you open your computer, or if you open your this one, what you call the charger of your mobile, capacitors are there, inductors are there, right? All are passive elements. It can be work for DC and AC both. A capacitor consists of two conducting plates. A capacitor is conducting of two plates. There is a parallel two plates will be there or circular plates will be there. But plates are important. Two conducting. Conducting means here no resistance. Very minimum resistance should be there. Two conducting plates separated by an insulator also known as dielectric. I place two plates like this. In between, there is air. What is air? This is a dielectric. It is a insulator. Current will pass in the air? No. Current will pass in the conductor only, semiconductor only, right? Air, wood, glass, etc. are there. These are the insulators. So between two conducting plates, we have to put some insulator, which is also called as dielectric. Then it will form a capacitor. Okay, see the shape. This is the first plate, this is the second plate, and this is the distance between the plates, and this in between is your dielectric R with a permittivity E. In resistance, what we have the name of the proportionality constant? R is equal to rho L by A, length, taksim, area. What is rho? It's the proportionality constant. Rho is called resistivity. Material to material, it will change. Resistivity. How much he has the capability of opposing the electrons. Resistivity. So here we call it as dielectric permittivity. Remember, resistance, length, area, resistivity. Here, capacitor, the same resistivity will come here as a permittivity. Okay, inductance will come. Three terms you have to remember. So permittivity and epsilon we call this symbol we use. Now these two are the metal plates where we connect the silk with the power supply, and it has the area. So it's same like resistance. It must have the distance, no length here. Distance, area. In resistance, length is the matter. Okay. When a voltage source is connected to the capacitors, means across these two wires, these two plates, across these two plates, if we connect a voltage source, then the source deposits a positive charge on the plate, on one plate, and a negative charge on another plate. See here. The same I have capacitor I connected with a voltage source plus minus V and to these two plates. So when we connect a voltage source, what happens? Due to this plus terminal of the voltage source, a plus positive charge is deposited, collected on a one plate on the left side. On the right side, where the negative terminal of the voltage source is connected, negative charge is deposited on that plate. So together it become a electric field or electric storage element. Okay, so next, so see the equations. Now we have to form the mathematical equations. The amount of charge, how much charge, the amount of charge stored, because in plus positive plate, one plate plus Q is stored. On another plate, minus Q is stored. One negative charge is stored and positive charge is stored. So what is the amount of charge? The amount of charge is represented by Q. The together complete charge, plus and minus together is represented by the roof Q, small q, and directly proportional to, and is directly proportional to applied voltage, because we are giving some voltage. So if you change the voltage, the charge will change. If you change the voltage, the charge will change. Increase, increase, decrease, decrease. So that is given by the charge is directly proportional to the voltage, and proportionality should be removed by a constant equal to. Then the constant is nothing but capacitance. Means the capacitor value is your directly proportional constant, the constant of the proportionality. So Q is equal to CV. If you increase the voltage here, the charge will increase. C is constant because once it is manufactured, it is constant. When capacitor is manufactured 10 microfarad, 10 microfarads only. Okay. So only we can change the voltage. If you change the voltage, charge will change on the capacitor. If you decrease the voltage, charge will decrease. So like this, we have Q is equal to CV. Important equation, just remember it. So where C is the constant of proportionality known as the capacitance of the capacitor. Now what is C in the form of construction? Like resistance R, V is equal to IR. R is the proportionality constant. What is the R value? As per the construction of the resistance, R is equal to rho L by A. Length, same area, and multiplied by resistivity. So like this, we have C equation also. Capacitance equation also. We'll see that one. So see here, same figure. Okay, the unit of capacitance is farad, capital F. Okay, C is equal to what is the capacitance? C, as per the construction of these plates and everything, what is it? What is the capacitance? This C is nothing but your permittivity epsilon naught O, epsilon naught R, A by D. For resistance, it was L by A, but here area by distance here. Area is equal because as per area increase of the plate, the capacitance value increase. Okay, there as the area increase, the resistance value decrease. This is a reverse here. So epsilon naught O, epsilon naught R, A by D. D is the distance between the plate. If we increase the distance between the plates, the capacitance will decrease because more distance, capacity charge transfer is more less. Charge transfer is less if it's more distance. Okay. So like our south, if you are shouting from here, okay, you can listen. If I go out and shout from there, you cannot listen. So this based upon the distance, the value of the capacitance will decrease. Where C is the capacitance, the capital C, A is the plate area in meter square, D is the separation between the plates, between the distance between the plates. Separation means distance between the plates in meters. Epsilon naught O is the permittivity of free space. Sometimes we have some free space in between, not only insulator, free space also will be there. It will act free space. That will also we have to consider. Nine, inductor, insulator also we have to conductor consider. So epsilon naught is a permittivity of free space. Epsilon naught R is relative permittivity of dielectric constant, means in between what we are keeping inside. Sometimes we may keep mica, sometimes we keep wood, sometimes we make porcelain. Many things we can keep inside as a dielectric insulator. So that value. Okay, capacitance is also given by another equation directly, but because fixed capacitance, packed capacitance doesn't have free space permittivity, no air inside. So what happens? E epsilon naught is zero, one. Epsilon naught is one. So I can rearrange the same equation with C is equal to epsilon naught A by D. A by D same here. Only epsilon naught R is coming. That is general I'm making. So epsilon naught means the value of the permittivity of the medium. Medium is here insulator or dielectric. So where A is the area of each plate in meter square, D is the distance between the plates in meters, and epsilon naught is your permittivity of dielectric material. That's it. Only one material we are using here, dielectric. We are not talking about free space. So these two is the equations. If they are not giving free space value, you can take as one. So only we can substitute epsilon naught R value. That's it. So capacitance definition. Capacitance is the ratio of the charge on the plate. Capacitance C is equal to Q by V. Capacitance is the ratio of the charge on plate of a capacitor to the voltage difference between two plates. Okay, easy. Q is equal to, oh sorry, C is equal to Q by V. Q is nothing but amount of charge on the plates per voltage applied across the plates. That's it. Voltage applied or voltage difference between the two plates. Across the plates, the difference between the plates are same, measured in farads. So this is about the definition and equation of the capacitor. Now we need voltage and current relationship, how it will behave. Typically, capacitors have values in picofarads. Pico means how much? 10 power minus 12 minus 12 or microfarads. Picofarads 2 micro means it may have micro 10 power minus 6, it may have nano 10 power minus 9 or 10 power minus 12. In these three ranges only, the capacitance values will be there, very small. Okay, the figure shows the circuit symbol for a fixed and variable capacitor. See here. So this is your A is a fixed capacitor, two parallel plates together. Don't put the capacitor far. No, it should be jumbo together only. With small space, not more. It is this one is your normal fixed capacitor, and this one when we have a saham, the arrow is there means it can be varied, it can be changed. Variable capacitor. The current is I and voltage across the capacitor what we are applying is V. Now, how to know that the capacitor is storing energy or giving the energy back? Capacitor, when it stores, it must give back also after some time. It cannot say that only it is storing. Battery, what is doing battery? Once they will charge and they will sell it to us. Then what happens? We use the battery, then it will discharge. Means it will give the energy to us, to the circuit, right? So somewhere it is already charged. So same capacitor also will do. What we will do, how can we know? Note that according to the passive sign convention, as per the sign convention, if V is greater than 0, the voltage plus as per plus minus and current is towards. V is greater than 0 and I is greater than 0, means I also flowing inside plus V is also more than 0, then or if plus minus is reverse and current is going out, means what? V is less than 0, I is less than 0. Then what happens? It tells that it is charging. Positive charge or negative charge charging it is. Now, if V is greater than 0 and I is greater than 0, or if V is less than 0 or I is less than 0, the capacitor is being charged, means it's storing energy. Now, if V and I less than V dot I together is less than 0, means the convention change. The current is outside and plus minus is like this. Then it is giving the power, means discharging or reverse. Current is inside, the V of is here plus and here is minus. Same thing, means it is giving the power. It's not storing the power, it's giving the energy. Okay, see the shapes of the capacitor. This is called your polyester capacitor, and this is ceramic. Do you know ceramic? Where we have the plates of the teacups, ceramic plates. So that's ceramic material. These are the two plates. Inside will be there. Inside the two plates will be there. Now this is called your electrolytic capacitor. Means in between there is a mica material will be there. Round plates will be there. So electrolytic capacitor. The different shapes are there. Only three I have shown here. These are fixed capacitor, not variable. Okay. Now coming to obtain current voltage relationship, okay, of the capacitor, we take the derivatives of both sides of the equation, which states that electric current is the time rate of change of charge measured in amperes. Chapter 1. We know the time rate of charge is nothing but current. I is equal to dq by dt, time rate of charge, okay, is nothing but current. So that equation we have to take. I is equal to dq by dt. Now we have to derivate, then substitute first in this what is q, then derivate. First substitute what is q. Q is cv, we already know. As per the capacitance, charge stored is nothing but c times voltage applied across the plate, cv. So substitute here cv, d cv. C will be constant, come out, dv by dt. I equal to c dv by dt is a new equation. I equal to c dv by dt, because I am replacing q with cv. Now, as per the definition, there I will derivate both sides. So derivate both sides. Okay. Now, if you take the I on the left hand side and on the y axis and on the x axis, dv by dt. This is the dv by dt. Then this is I. How the slope is there? A linear slope, constant slope. Okay, linear slope. It's a, so that's why the capacitance will act as a passive element, linear element. How? Based upon this slope. Same thing. V is equal to IR. I and V if you use, then R also, so slope is same. But here V is not exact V. Here derivative with time, change with the time here. So the slope is C. So the equation I is equal to C dV by dt. From this current and voltage relationship also we can tell. Now, the relationship illustrated in this figure for a capacitor whose capacitance is independent of the voltage. Whose capacitance is independent means capacitance is not dependent on voltage. Okay? Capacitance is fixed. It's not depending. If we change the voltage, current will change. If we change the voltage, charge will change. But C will not change, independent of the voltage. Okay, capacitors that satisfy this equation are said to be linear because the slope is linear. That's why, like a resistor, capacitor also a linear element. Linear element. Now coming to capacitor, I is equal to C dV by dt. We know now. Capacitor operator integrate both sides. You integrate. So what happens? If you integrate means what? They take the dt on this side and C dVp on the right hand side. So integrate both sides I dt. So just I want in terms of V. So I dt CV will be there. I dt CV will be there, and dV. If you integrate the dV, this dV if you integrate, what happens? V of t it will come voltage. Now the C take on the left hand side. C take on the left hand side. Then 1 by C. This I dt will become I of tau and d tau from minus infinity to some time, means in future some time, minus infinity to in future some time. Okay, just did you understand here what I did? Integrating means how? I dt, when take the dt this side, I dt, I take the C on the left side, 1 by C. Now integrate both sides, dv will become V of t. Then 1 by C I of t integration means integration from minus infinity to the future time I of t dt or d tau we can say. Now when it is minus infinity to t is there, we have to see the initial value condition. Integration always have its integration plus its initial value. Already you studied in calculus 2. Integration, differentiation, there is no initial value. But in integration, when you integrate it, there should be an initial value, then integration. So like that. So same here, V of t0 means initial value. So from that initial value to the some time, the same equation I of t dt will be there. Now what is V of t0? Initially, is there any charge inside the capacitor or not? That we have to see. So where V of t of 0, this one is nothing but Q of t per by C, because you, what we call V is Q is equal to CV. So V of t is 1 by C Q of t. So Q of t is 0 is nothing but your initial value, initially what is the charge inside the capacitor, the same the capacitance. So that is the initial value of the voltage. That voltage will come here. Now the instantaneous power, what is the power now? So we got the voltage equation, we need the power, then we need the energy, then we will stop there. So V of t, we know it. Now what is the instantaneous power delivered? P, for P is equal to VI. P is equal to VI, already we know. Substitute, what is I? V is as it is, what is I? C dV by dt, C dV by dt. So C V dV by dt. Now this is your power. Now next, now the energy, power got, we got it. Now we need energy. Energy means energy content. Rate of change of power is energy, right? For some time. So the energy stored in a capacitor, therefore, what we have to do? Integrate. Energy is nothing but integrate. Integrate with P is nothing but your W. That is energy. So it is integrate from minus infinity to some time T. Then the power P of T is nothing but your energy. Now P of T already we know CV dV by dt. Now substitute here. C is a constant. Take it out. Now V dV by dt d tau. Now d tau will cancel. Okay, dt will cancel. Only V dV integration will be there. So C we now, because previously it was with the time, because we are integrating with time, so dt cancel. Now only voltage is the variation from minus infinity to the some point of that voltage. So see, voltage from minus infinity to the voltage for some time. So v dv, so we only v integration, x integration. What is x integration? X square by 2, 1 by 2 x square, x integration, x power 1 plus x power 1 plus 1 same by 1 plus 1, that is x square by 1 plus 1, that is 2. So here also v is like a x, so v integration is nothing but v square by 2. See, v square by 2. So c was there, c multiplied by half v square, range from v infinity to v of t. But we know previously when it was manufactured, infinity means minus infinity means the Qadim, very old. When it is manufactured, the capacitor, is there energy stored inside? No, because we didn't give any voltage to that one. So it is 0. So initial value is 0 now. So what happens? We know that V at the infinity point, minus infinity Qadim point is 0 because there is no charge inside. Because capacitor was uncharged at t is equal to minus infinity. When it is manufactured, there is no charge. Just we put the two plates, we put the dielectric, we sell it. So there is no charge. So that's why it is 0. Initial value is 0 because we are doing integration here. So this one is 0. Now only V of t we have to take. Then the equation will be given as W, that is energy stored in the capacitor, is equal to half CV square. At any time, half CV square is your energy. This is the one equation. 3 equations you have to remember. First one, Q is equal to CV, capacitor times voltage. Second one, I equal to, sorry, this one, P is equal to VI, that is C dV by dt. Now power. Now voltage, energy is equal to half CV square. These 3 important equations you have to remember. Now using equations 6.1, that is Q is equal to CV, we may rewrite. Just now again rewrite in terms of charge. Sometimes we don't know what is V. We know only how much charge it is there. At the time what happens? See here. W is equal to half C V square. What is V square here? V square is nothing but Q by C whole square. Q square by C square. So substitute here Q square by C square. Then C will cancel. Means 1 C will cancel. Then 1 by 2 C V Q square will come. Q square by 2 C. Because V square is nothing but Q square taqsim C square. So Wahid C will cancel. So W energy in terms of, see, you know this equation Q is equal to CV and you know the W is equal to half CV square, then it is easy. You can just resubstitute it, you can get the new equation. That's not a big deal. Okay, now 6 point, these 2 equations represent the energy stored in electric field that exists between the plates of the capacitor. Between the plates of the capacitor, how much energy is stored is given by these 2 equations in terms of voltage, in terms of charge, anything. Okay, now we should note the following important properties of capacitor. What are the properties? We know that it can store the energy. Furthermore, what we know? A capacitor is an open circuit to DC. If you give the DC circuit, DC value, it will act as open circuit. Why? Because two plates are there, in between dielectric is there. So dielectric will act as a open circuit. Okay, it won't pass any current. Open circuit means what? No current passing. It will store the energy in terms of charge and it will give back, but it won't pass the current through those two plates in between. So it is act as open circuit for DC. But for AC, it is different. You will study there. It will give the power back. It will store and will give back. Both possibilities are there. So a capacitor is an open circuit to DC. The voltage on capacitor cannot change abruptly. The voltage on capacitor, instantly we cannot change. It will take some time. If we give 5 volts, it will not change. It will not, at that instant itself, it will not give, because it will take time to travel. It will to deposit on the plates, then the voltage will form there. So it cannot be changed abruptly. The ideal capacitor does not dissipate energy. I already told, resistor dissipates energy, wastes the energy. Capacitor and inductor stores the energy. So ideal capacitor, exact ideal capacitor. This is ideal capacitor is not possible in the universe, because anything has some leakage, some non-ideality. So a real non-ideal capacitor has parallel model leakage resistance like this. So actually ideal capacitor only these two plates and this is the shape. But in practice, in practical, always it has a leakage resistance which dissipates some energy. Means it have, because resistance means what? A silk. It has some resistance. R is equal to 0 doesn't have any value. R is equal to 0. If you manufacture a conductor, means it has some resistance. If you are manufacturing two plates of capacitor, means this plate has some resistance, this plate has some resistance. Okay, so that resistance will act as a leakage resistance. Okay, sometimes that leakage is so small that we just neglect that one. That is different issue. Okay, now example calculation we have, very good. We can very easy calculations. Calculate the charge stored in 3 picofarad capacitor with 20 volts across it, direction, and find the energy stored in the capacitor. Already given what is 3 picofarads. What is it? C, capacitance value, picofarad. Pico means 10 power minus 12. Now, how much voltage? 20. So we have one simple equation. What is the equation? Charge equal to C times voltage. Just multiply it. It will get it. Then find the energy stored in the capacitor. What is the energy stored? W is equal to half CV square. Right? If we have voltage, C we have, V we have, half CV square. Just apply it. Since Q is equal to CV for the first answer, multiply it. 3 is the picofarads, 10 power minus 12 is your capacitance, and V is the 20 volts. So the multiply 60 pico coulombs. Okay. The charge is in coulombs, charge unit. Now energy. W is equal to half CV square. Half C already you know 3 picofarads 10 power minus 12, and V square 20 power 2. 20 multiplied by 20, 400. So 600 picojoules. Energy always stored in the joules. Okay, or watts. Okay. The voltage across 5 microfarad capacitor is. Now this is not telling that is it DC or AC voltage. How can you know this is DC or AC voltage? This is DC supply or AC supply. How can we know? By seeing the voltage. How much voltage it is? 20, a constant voltage. No sign equation there. Then it is a DC. Now here the voltage is instantaneous. Time to time it is changing. V of t means instantaneous. So V of t is 10 cos 6000 t. Means this is a fixed value 10, and cos 6000 t is changing value. Cos means how much? Like this. Cos, it will start from 90 degrees. Sine means it will start from 0 degrees. 0, 90, 180, 360 like this. Cos V of t is nothing but your 10 cos 6000 t volts. Now calculate the current through it. What is the equation? If we have voltage and we have C and V, what is the equation for the current? I is equal to C dV by dt, correct? I equal to C dV by dt. So now substitute C, or is it 5 picofarads? dV by dt. d by dt of what is V? 10 cos 6000 t. Now differentiate this cos. 10 will not be differentiated, it will come out. Then it will become 5 10 power minus 5. Then cos 6000 t. Cos 6000 t differentiation. Cos 2x differentiation. What is the differentiation? The 2x, the 2 will come out, and cos is differentiation, sine. Sine 2x, and cos is minus or plus? Minus sine. Okay, cos is minus. See, minus is coming out because cos is differentiation minus sine. But inside what is there? Inside it is 6000 t. So this 6000 will come out, and cos 6000 t will become sine 6000 t. So this 6000 is coming out, and this 10 is not differentiating because it's coming out. This 10 is there. So 6000 multiplied by 10 and c value 5 into 10 power minus 6. And due to the cos is differentiated, it is minus and it is sine. So the value is 0.3 sine 6000 t amperes. So this is how the simple problems are there. Now we have bigger problem. How? Let's see. Determine the current through 200 microfarad capacitor whose voltage is given figure. Previously, it's given the cos equation. Now let us take the equation is not defined. The equation is in different other form. What is that form? Check here. This is called triangular wave. Okay, this is called triangular wave. For any wave, first we have to find the equation for that wave, then substitute time to time what are the values, then you can get the instantaneous values. So here, so what we need? Current we need. Same, current is equal to C dV by dt. This is the voltage. C dV by dt. We have to differentiate for each point. 0 to 1 we have to differentiate. 1 to 3 we have to differentiate. 3 to 4 we have to differentiate. So first we will write the sub blocks. What is it? We know that waveform, that what you call triangular waveform equation is this one. V of t is nothing but V1 plus V2 minus V1 divided by T2 minus T1 and T minus T1. So this is your equation for the triangle. Okay. Now for each step, each second, we have to find what is the voltage. Then we can go for the finding current. So how it will be set? From 0 to t, from 0 to 2, the slope is like this. So substitute the values here. 0 to t, 0 to 1, 0 to 1. What is the values? V1, how much? At 0. V1, 0. Now V2, how much? At t is equal to 1 second. Come see, 50. What is V1? 0. So 50 minus 0, it's 50 only. T2 minus T1. What is T2? 1. T1, 0. So 1 minus 0, 1. So 50 by 1, 50 only. Now here, T minus T1. What is T1? 1. T minus T1, sorry, T1 is 0. T minus 0 is T. So here 50 times T and V1 is 0. So what is the voltage? 50T. Just substitute these values as per this slope. What is awwal, what is akhir. Then substitute here, you will get the equation. Now second one, from 1 to 3, because it is only one slope, 1 to 3. You can tell 1 to 2 also we can take, or 2 to 3 also we can take, up to you. The values will increase. Okay, 1 to 3, it is same slope. So check here. Here one slope from 0 to 1. But 1 to 3, it is same slope. So we can take the time period 1 to 3, not 1 to 2 and 2 to 3. Just 1 to 3 we can take. Next, 3 to 4 we will take, because one slope. So 1 to 3, when substitute here, at V1, at time 1, what is V1? Come, 50. Just substitute here 50. Now, V2, at time 3, V2, time 3, minus 50. Substitute here minus 50 minus V1, 50 at time T1, 50 minus of minus 50 minus 50. How much? Minus 50 minus 50 minus 100. Okay, remember fluid. This become now minus 100. Okay, now here plus 50, here minus 100 divided by T2 minus T1. T2 is 3, T1 is 1. 3 minus 1, how much? 2. So minus 100 divided by 2, how much? Minus 50. Okay, here plus 50, here minus 50 times times T minus T1. What is T1? 1. So T minus 1, times minus 50. So minus 50t plus 50t plus 50, right? Minus, because one t minus 1 other. T minus 1, here minus 50 is there, zarb. So minus 50 t मौजूद. Minus 50 minus 1 plus 50. So here plus 50 and this V1 plus 50, 100. And remaining minus 50t. This is the second. So 100 minus 50t. Now 3 to 4. 3 to 4. Substitute. What is V1? 3. At the time of 3, what is V1? Minus 50. What is V2? 0. 0 minus V1. Minus V1. What is V1? Minus 50. Minus of minus. Plus. Right? 0 minus of minus 50 plus 50. So here only 50 is there. Okay? Here minus 50. Here plus 50. Divided by T2 minus T1. T2 is 4. Minus T1 is 3. 4 minus 3. 1. So here 50 only. Plus 50. Here minus 50. Here plus 50 times T minus T1. What is T? T only. T1? 3. T minus 3. Okay, now Zarbada. How much here? Plus 50, right? Plus 50 times T, it is there. Plus 50T. Now plus 50 times 3. Minus 3. So minus 150. Minus 150. Minus 150. Here V1 minus 50. Total minus 200. So like this we'll get. So after greater than, otherwise, bad hada arba kulusifar only. No need. So now this is the voltage we got. Now we need the current. First we have to know what is voltage. Then only we go for the current. So current is given by I is equal to C dV by dt. I equal to C dV by dt. C is equal to 200 microfarads already given. Now C dV by dt. Just differentiate dV by dt. We know it. V is every time is changing. So differentiate 50t. When you differentiate, what is the value? X. Dx by dt. What is it? 1. Dx by dt is 1. Right? So t will go. Dt by dt is t will go 50. Right? Now second one. D by dt of 100. Constant. Any constant differentiation is 0. So this will become 0 minus 50t dt, d by dt of 50t, t will cancel. So 50 only will come, that is minus 50. Only minus 50 t is going. Now here, minus 200 differentiation, 0. Plus 50t differentiation, t will go, 50 will come. 0 means 0. So this is your differentiation of dv by dt. Now C dv by dt, C is already there. That is 200 into 10 power minus 6. And these are the different ranges. Now multiply. When you multiply this for each items from 0 to 1, 1 to 3 and 3 to 4, 50 into 200 and 10 power minus 6, you will get 10 milliamperes. Okay, 2 zeros and here 1 zero will become 10 power minus 2 will become 10 power minus 3. 10 power minus 3 is nothing but milli. Okay, 5 into 2, 10. So 10 milliamperes. Here minus 50 is there, so minus 10 milliamperes. Here plus 50, it is 10 milliamperes. Now it is 0. Now you tell me, previously this is your shape of the voltage. Now how the shape of the current will be? See here, 0 to 1. What is the value? 10. 10, 0 to 1 means from Sifar Tania ila Wahid Tania, the current is 10, right? How much? Constant. Here 50t previously in this one means slope is changing. But here 10, there is no time here. Just 10 means constant value. So 0 to 1, 10 milliamperes constant. Next, Wahidilla Talata, 1 to 3, how much? Minus 10, that's also a constant. There is no t value there. So Tahat constant. Next, 3 to 4, how much? 10 milliamperes, that's also constant. So how the wave will be? See. 0 to 1, how much? 10 milliamperes constant. Next, it is going 10 to, directly it is going to minus 10. Where? Down. 10 to is going to the minus 10 and it is constant till t is equal to 3. Till 1 to 3. Then again, from minus 10 to, it is going to the plus 10 and constant till t is equal to 4. So like this, you have to form the waveform from triangular to uh, in the current waveform. Now it is which waveform it is called? Which one it is? Rectangular pulse. Pulse we call it. We call it is. Okay. Next. Okay, last topic, series and parallel capacitor will finish and we'll stop it. So how the series and parallel combination of the capacitors will be worked as? We know the resistance. When the two or three resistors are connected in series, what is the equivalent resistance? Just R1 plus R2 plus R3. We know it. When the two resistors are connected in parallel, what is the equivalent resistance? R1 into R2 divided by R1 plus R2. This is your equation. Here, quite opposite. In series, R1 plus R2 plus R3, like that. But here it will come it as a parallel. When connected in parallel, C1 plus C2 plus C3 plus C4 will come. When in parallel in resistance, R1 R2 by R1 plus R2. But in capacitor in series, it will be the same equation. Just opposite to the resistance. See here. To obtain the equivalent capacitor, C equivalent of n capacitors in parallel, consider this circuit. 1, 2, 3, and up to n capacitors are there in parallel. Then it is nothing but summation of all C1 plus C2 plus C3 up to n. It is given as the equivalent capacitance of n parallel connected capacitors is the sum of the individual capacitances. C1 plus C2 plus C3, all capacitances together is nothing but C equivalent. So we can write this in terms of like this. So C equivalent is equal to C1 plus C2 plus C3 up to Cn. This is one form. Quite opposite to the resistance. Now same. We now obtain n capacitors connected in series. Previously parallel, now we connect in series. Then how it will be? Let's check. C1, C2, C3 are in series. All voltages are there, V1, V2, V3 up to Vn. Some main voltages applied here with source. Then how the equivalent capacitance. And note that capacitors in series combined in the same manner in parallel. But now the equivalent capacitance of a series connected capacitor is the reciprocal of the sum of the reciprocal of the individual capacitor. In resistance, if we have many capacitors in parallel, what we will do? First, we will take the reciprocal x of each capacitor, then we'll jama kullu, then x. Three steps. First, each capacitor reciprocal x, jama kullu, then maratani x. So that is your equivalent resistor. Same here for series also. See, 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by Cn. Again, if you want C equivalent, X of Kullu. Okay. Okay, for two capacitors in series, C1, C2 divided by C1 plus C2. That is 1 by C1 plus 1 by C2. Now C equivalent will be C1, C2, C1 plus C2. Then X, C1, C2 divided by C1 plus C2. Or C1 multiplied by C2 divided by C1 plus C2. So how it will be? It will be look like this. So like this, we have series and parallel combination. One example we'll study and then we'll stop. Find the equivalent capacitance seen between terminals A and B of the circuit. Easy. Many capacitors are connected in series and parallel. Now start from the left hand side because we want the output at A and B terminal. So start with the left hand side. These two are in series. 5 and 20 are in series. So what is the equivalent? Zar, Taqsim, Jama. Series. Because opposite to the resistor. It is in series, Zar, Taqsim, Jama. So find it. 20 multiplied by 5 divided by 20 into 5. 20 plus 5. So 25. 5 5 is okay, 5 4 is Arba. 4 microfarads is the series equivalent. Now 4 and 6 are in parallel. So what is the equivalent? Just Jama. 4 plus 6. How much? 10. So it will become now up to here it will become 10 microfarads. Now 10 and 20 in parallel. Same. 10 plus 20 because these are in parallel. 30. So 30 and 60 are in series. For series, what is the equation? Zarb Taqsim Jama. So 30 plus 60 divided by 60 into Zarb 30 into 60 divided by 30 plus 60. That is 90. 30 into 60 divided by 90. Okay. It will come, I think. Okay, what it will come? Yeah, 20 microfarads. Sorry. Yeah. So first one is 20 and 5. This 20 and 5 in series. So the Zarb and Jama Taqsim. So 4 micro. Now 4 micro, 6 micro and 20 micro are in parallel. So total Jama 6, 4 plus 6 plus 20, 30. Now 30 and 60 are in series. So 30 into 60 divided by 30 plus 60. So 30 into 60 by 90, it will give 20 microfarads is the equivalence. So now inductors we'll study in the next class, inshallah. Okay, let's start. So today topic and chapter 5 we'll finish. In last class we studied about the capacitors, it's their property, its construction wise, what is the equation, and how the voltage and current relationship will be there, and some problems on it. And we studied about the series and parallel combination of capacitors and how to solve that. Same topics will come in the inductors also, same topics. And inductors, what is the definition? An inductor is a passive element designed to store energy in its magnetic field. So in previous class I told you resistor is a passive element which dissipates energy, means waste energy. Maybe it may give through IR radiation or heat, something. But capacitor inductors are passive elements, but they store energy and give back energy that whatever stored it can give back to the supply also. So this is a passive element. It stores the energy in magnetic field. Unlike capacitor stores energy in electric field. Here inductors store energy in magnetic field. Electric field means what? Charge. Magnetic field means what? Current. Okay. Due to the current and coil, a magnetic field will be generated. Ampere's law, Thumb's rule, Thumb's rule. We'll study that. Inductors are used extensively in power supplies, transformers, radios, TVs, radars, and electric motors. So, on these applications, inductors we have. You can see in any device, open it, computer also, you can open it, their inductors will be there. And TVs also, very powerful inductors will be there inside. And we have radar system to track the aeroplanes or track the air objects. It is there. So we use that one. And motor is basically inductor. Electric motor is basically a inductor. An inductor consists of coil of conducting wire. So inductor is nothing but a silk, that is a wire. When it is rotated on a what you call material, maybe iron or some different type of material, or air core also, means like just to rotate a wire in a air and connect some supply, it will give some current and magnetic field. It will pass a current, and the current, due to the Ampere's law, develop a magnetic field. And now the another method is put inside a material like iron, cast iron, or many different alloys also there. That material, if you put in inside the wire, then it will be more powerful inductor. So it is a coil. Basically, it is a coil, means rotated wire. Means it is rotated wire. It is a coil. I will show that diagram. See here. So this is your inductor, and this is your core material. This core may be the air or any other material which is act as a medium for the supporting the wire, and it will act as a medium for the transfer of the magnetic field. Now this wire have some turns. Turns means one rotation, first turn, second rotation, second turn, third rotation, third turn. So like this, number of turns we call, how many times it is rotated, turns. So as per the knowledge, as per this diagram, we have how many turns? We can count it. More than it is 20 turns we have. So that is nothing but your number of turns. Now length. Length means how much is the length of that core is your the length you will call, and cross section of that core. Once you turn is finished, the cross section what it is making, that is called cross section area. So using these four values, one is length, area, and turns, three items. Another is called permeability. Like your permittivity in your capacitor, there is a proportionality constant. Here we have a proportionality constant, permeability. So four items we need here. So Formula for calculating inductance of inductor of different shapes are derived from electromagnetic theory, which is not important here. We just remember this the formula. What is the L? It is denoted by capital L inductance and measured in henries. L is equal to N square. N is nothing but your number of turns. How many times it is rotated? N square means power 2. N square area, observe area and taksim L multiplied by area and divided by length L. And here the proportional constant mu is there. It is called mu. It's not micro. It is a mu, one letter mu it is. Okay. So that letter name is called where is that? Mu is called permeability of the core. The material what we are using. Sometimes we may use air as a permeability. Sometimes we use iron as a permeability. Sometimes many alloys mix it and we use it for good performance. So permeability of the material means material property you can say. So like this we have to remember this equation. What is the equation for resistance? R is equal to rho L by A, length divided by area. And what is the equation for the capacitance? Rho epsilon naught epsilon naught epsilon naught 0 and area by length. Sorry, what is it called? Area by distance. The distance, there is no length here. In the capacitance, the distance between the plates will be there, A by D. Okay, this opposite to the resistance. Now in inductance, what do we have? L is equal to A by L, you remember. A by L and N square. Then permeability always there. Some constant will be there, proportionally constant. N square A by L times mu. Now come to the voltage and current relationship. If current is allowed to pass through an inductor, if a current is allowed to pass through an inductor, which is a wire, basically it's a wire. So a current can pass through a conducting wire. So when a current is allowed to pass through an inductor, it is found that the voltage across the inductor means across the complete turns, voltage across the complete turns, that is voltage across the inductor is directly proportional to time rate of change of current means how much the current is changing with that time. Now how much? After 1 second, how much? After 2 seconds, how much? Time rate of change of means di by dt. Time rate of change of current using the passive sign convention means current is flowing on the left to right side or right to left side. That is passive sign convention is given by the voltage is given by proportional. The voltage is proportional to di by dt. But if we want equality, then we have to multiply with a inductance, the value of that material inductance. So where L is the constant of proportionality called inductance of the inductor. And you know what is L? That is L is nothing but N square mu L by A by L. The unit of inductance is henries. So inductance is a property whereby an inductor exhibits opposition to the change of current flowing through it. Means it is always opposed the change of current flowing through it, measured in henries. dA by dt is nothing but your change of current only. Means how much is changing due over a time. So the circuit symbol for inductor are shown in figure and following the passive sign convention. Check here, there are three different types of circuits symbols are there. First one is a coil, it is shown here. Plus minus is the convention and current enters through the plus means it is a positive value. Means it is charging, positive value. And voltage across it. Now there is another same, all are same. The convention is same. Current is entering at plus means it is a inductor is charging. But why the shapes are different? Okay, I can understand. The saham, the arrow is showing that it is a variable inductance. We can change the value of the inductance at time to time as per our application. But why these are two different here? Here inductance is only coil. The turns are there. But here coil is there. Two lines are there. What is the meaning of two lines? We have two types of inductors basically. One is called air core, means inside the coil, the coil is in the air. Here the coil is on the core. Core means maybe the iron material, maybe the alloy of the many iron material. There will be a hard hadith. Hadith we call the iron. There will be a coil on it. Then it, the iron, the hadith is called as core. That core if we have, then that is given by a two lines. That is given by a two lines. Some inductors are there without core, just hawa in the air. It will be there rotated. That's it. Inside there is nothing is there. You can pass air inside. Okay, so that is no lines. Here no lines are there. Two lines are not there. So like this, we have three different shapes of the inductors. One is air core inductors, and second one is iron core inductor. The third one is variable iron core inductor. Okay, next coming to the voltage and current relationship. We know what is voltage in terms of current, that is V is equal to L di by dt. Now we have to derive till power, voltage, power, and energy also. So the current voltage relationship is obtained from equation, the previous equation, that is V is equal to L di by dt. Now rearrange that one. The L will be go other side. It become 1 by L V. Di by dt, I am just taking the dt to this side. Di is on the left side. Just rearrange the previous equation. L di by dt equal to V. So dt and L take other side. Di keep in the same side, di. So now we have to integrate. Now integrating both sides will give integrate di will give I. Now integrate v dt. So we have to integrate this voltage from minus infinity to the some time v of tau d tau. Means we are integrating. Now when we are integrating, what should be there? There should be an initial condition we have to take care. So we will see that one. So we can write this integration 1 by L t0 to t means starting time to the end time, that is v of tau dt d tau plus I of t0. What is t0? It is a initial condition. When we are starting at the initial condition, what exactly already available the voltage inside the inductor. That is I t of tau means the current already stored, means or the energy, the what we call inductance already stored inside the material, means some inductance already stored means it can be driven back to the supply in terms of current. That is initial condition I of T0. But at the initial condition where I of T0 is the total current from minus infinity to the initial condition, minus infinity to initial condition, and at minus infinity, I of minus infinity is equal to 0. When it is manufactured, there is no charge inside the wire or inside the inductor, so it is 0. So I can take it as I of T0 is equal to 0. So because there must be a time in the past when there was no current in the inductor. There is no current in the past when it is manufactured, or in the past very long back, then it will be 0. So this I of T0 becomes 0, only remaining this one. So it becomes the inductor is designed to store energy in magnetic field. The energy stored can be obtained from equation, the previous equation, and the power delivered by the inductor is P is equal to VI. So what is V? We know L di by dt. So substitute here what is V? L di by dt multiplied by I. So now the energy is stored. Once we know the power, then we have to know the energy. Energy is nothing but integrating the power from 0 or from any initial value to the some time. So integrate from minus infinity to t to this power, that is Vi, that is L di by dt times I. Okay. Oh, sorry. So the energy is given by the integrate from minus infinity to time t to the power. Means we have to integrate the power. So substitute the power equation L di by dt times I here. So L minus infinity to t and di by dt I d tau. So we have to integrate I. Okay, di by d tau is that d tau will cancel, and I di will be remain. So I we have to integrate. So I integration, x integration is nothing but x square by 2. So like this, I square by 2 will come. So just substitute here. So I di. So half L I square t means half will come here. So I square by 2. So half Li square at the time t and minus half Li square at the time minus infinity when it was a very old value. The initial condition also we can say. So but this minus infinity from the previous section we can say it is 0. So directly we can give energy stored in the inductance is nothing but half Li square. It is same equation apparently with the capacitor. What is the energy stored in the capacitor? It's nothing but half CV square voltage relation. There is a electric field. Here magnetic field. Electric field always relate with the voltage, half CV square. Magnetic field always relate with the current. So half Li square. Equation is same. Only their voltage here current. Their capacitance here inductance. Okay. So this you can remember. You can if you correlate, then it will be easy to remember. So like this, we have power equation, we have energy equation, we have current equation and voltage equation. Now go to the some points. We should note the following important properties of an inductor. An inductor acts like a short circuit to DC. Unlike capacitor, capacitor will act as a open circuit to the direct current. If you give the direct current, constant current, it will act as a open circuit, capacitor. Inductor will act as a short circuit. Means whatever the current is there, it will automatically flow directly. It won't stop anything because time rate of change of current is the inductor, the voltage. So it current when it is changing, then only inductor can store the energy. But in the direct current, DC current, current is constant. It's not changing to maximum value, minimum value. It's not changing. So it will act as a short circuit. Means whatever the current is there, it will flow through it. It won't stop anything. So the current through an inductor cannot change instantaneously. In the capacitance, the voltage cannot change instantaneously or abruptly, but here the current cannot change instantaneously. That's why it will act as a short circuit when it gives DC. Okay, the ideal inductor does not dissipate energy. Same like capacitor, it does not waste the energy. Dissipate means waste the energy. Here also inductor, ideal inductor means pure inductor cannot waste the energy. Whatever it will store, it will give back. Same like capacitor. A practical or non-ideal, but in the universe we don't have a we don't have ideality. Means inductor means it has some non-ideal, means some problem is there, means some leakage is there. Capacitor also some leakage is there. So this is called non-ideal. So a practical non-ideal inductor has a significant winding resistance because we know that the wire, when wire is rotated, we have some length of the wire. So when wire is coming into the picture, we have some resistance in it because conductors we have some resistor. So that winding resistance we call. Due to that, we have a leakage. Leakage means we have some energy dissipation due to the conducting materials resistance, that is called due to the resistance of that wire. Winding capacitance, in capacitance is not coming, but here why is capacitance coming? Because when wire is rotated, two wires are coming in together in parallel. So when two wires are coming in parallel, in between there is a medium, dielectric medium is there, maybe air, maybe core, whatever. So when it will act as a two plates, when it will act as a two plates together, with a small dielectric material in between, it will act as a capacitor. So how many turns are there? Divided by 2 if you make it. Then that many capacitance it will fall. It will generate. So that will also have some problem. We can agree that it has very small value, but it will have. So due to the capacitive coupling between the conducting coils means the turns, between the turns, we have a capacitive coupling, means capacitance it will be formed. So they are usually very small, so they can be ignored in most cases. So small that we can ignore also. But if we need exact minute values, then we can think about it. We have to include it. So where L is the main inductance. So I know due to these turns, the length of the wire, we got a resistance. This is called winding resistance. We call winding. The turns is called as a winding. So it is a winding resistance, and we got due to these three, 1 and 2 turns, these two turns. How many? 1, 2, 3, 4 capacitances are forming. So these capacitances will generate a winding capacitance. See, they are very small value. Due to this, very small power loss will be there. You can neglect also. So like this is the circuit model of non-ideal inductor. Ideal inductor, only the inductor. That's it. L. Now come to the example problem. The current through zero point 0.1 Henry. Inductance always will have in millihenries to henries only. It doesn't have micro, pico, mega, kilo. No, it have milli to just henries. So 0.1 Henry inductor is the current inside the inductor, the current is flowing is I of t is equal to 10 t e power minus 5t. So this is a some time change of current, it is there. It is not a DC current. So when it is not a DC current, inductor will act inductor only. If it is a DC current, let's for example, if it doesn't have t e power minus 5t, just only 10, I is equal to 10 amperes, then what is it? It is a DC current. In DC current, inductor will act as a short circuit. Doesn't have its effect. It can't store energy. Okay, it must have a some time rate change. That is, here we have time function t e power exponential function we have e power minus 5t. Sometimes for sinusoidal cosine we have sine, some terms cosine terms will be there, cos theta, sine theta, like that. That also it can store the energy. Okay, tan t e power minus 5t is your current flowing through the inductor. Find the voltage across the inductor and the energy stored in it. Find the voltage across the inductor and energy. We need two items. So what is we need? Voltage. Voltage is equal to V is equal to L di by dt. That is the voltage you can find. What is the energy? Half Li square. If you know I, you can half Li square. Or you can integrate by power equation P is equal to Vi. You can integrate there also. From time to time, we can use anyone you can use. But here half Li square is best suited. So what is first one? We know that V is equal to L di by dt, and we know L is 0.1 henries. 0.1 henries is the L. In this di by dt, we can find from the 10 t e power minus 5t by differentiating the I. So if we differentiate this one, UV method, AB method, it will differentiate, it will come like this. So 10 will come out, it become 1 t e power minus 5t, AB. Differentiate AB. Then first differentiate A, keep the B as it is, plus differentiate B, keep A as it is. That is the rule. So first differentiate T. So in the first, we got two terms, A plus B terms it will come. So first differentiate T, then it will become e power of minus 5t and 1. Those are e power of minus 5t. 10 into 0.1, 1. So e power of minus t when we are differentiating T. Now second time, we have to differentiate only e power of minus 5t. T is as it is. So T will be come out and 10 and 0.1 will become 1. So T differentiate d by dt of e power of minus 5t. If you are differentiating e power of minus 5t, the minus 5 will come out and e power of minus 5t will be as it is. So t is the previous case, that is as it is, and e power of minus 5t, if you differentiate, minus 5 is coming out, that is minus 5 e power of minus t as it is. So t minus 5 times e power minus 5t. So total, if you take out the e power of minus 5t, then it will become 1 because of the minus 5, it become minus 5t. So this is your equation for voltage. We got the voltage equation. Okay. Now coming to the energy. Energy stored is nothing but half Li square. So what is half Li square? L we know 0.1. Half we can keep it here. I square. What is I? 10 t e power minus 5t. We can substitute here. 10 square. How much 10 square? 10 square is nothing but 100 power 2. 10 square is power 2, that is 100. T square, t power 2, t square. And e power minus 10t, minus 5t power 2. So it will zerp, 5 into 2, 10. So minus 10t. So this is your final equation. 50 into this one, 0.1, it becomes 5 t square e power minus 10t. Okay. 50 into 0.1, it is 5 t square e power minus 10t joules. This is your energy stored. So like this, we have to find the power voltage and the energy. Now we have another example. Find the current through the 5 henries. Here 5 henries inductor is if the voltage across it 30 t square and 0. That is for t is equal to greater than, means more than 0 time, it is 30 t square. Before the time that is less than 0, then it is 0 only. So initial condition is not there here. Okay, I also find energy stored at t is equal to 5 seconds. Assume I of v greater than 0. Means after the t is greater than 0 only, we have to calculate at 5 seconds. Okay, same the previous method also we can use. So what is current? I is equal to voltage is given. Now we need the current. Previously current is given. We have to find the voltage, the differentiation. There is V is equal to L di by dt. Now we need the current. not the voltage is given. So integration we need. So same L di by dt, if rearrange, it will become 1 by L v dt integration. So I is equal to 1 by L t0 to t v of t dt, and initial condition I of t0. Initial condition I of t0 is 0 here. Just we have to integrate 30 t square, and L is given 5 henries. So I is equal to 1 by 5 because of the inductance is 5 henries. Now 30 t square is the v of t, 30 t square dt plus 0 because initial condition is 0 here. Now t square integration, x square integration, x integration is x square by 2. X square integration, x power 3 by 3. That is x power n plus 1 divided by n plus 1. So that is x power 3 by 3. That is t square integration t power 3 by 3. So this 30 divided by 5 is nothing but 6 times t power 3 by 3. That is 2 t power 3 is the amperes I. So this is your current for this time period more than t is greater than 0. Now the power P is given by VI. VI is nothing but 60. V already we know what that is 30 t square. What is I? Is nothing but 2 t power 3. So 2 t power 3 multiplied by 30, that is 60. 60 t power 2 and t power 3, t power 5. So 60 t power 5 power. Once we know the power, just integrate the power from up to at what second? 5 seconds, from 0 to 5 seconds. So integrate this power to 0 to 5 seconds, then you will get the exact power energy stored, energy stored in the inductor. So 60 t power 5 dt. So t power 5 integration, any power integration is nothing but that power plus 1 divided by power plus 1. So t power 5 will become t power 6 divided by 6. So 60 t power 6 divided by 6 from 0 to 5. So 0, leave it. 0 is initial condition, it will not come. Only substitute 5 here. 5 power 6. 5 times, 5 times, 5 times, 6 times you have to multiply, and multiply with 60, you will get 156.25 kilojoules. Another way also there. What is another way of finding energy? We have direct equation. What is that? Half Li square. This is a final equation. No need of any integration, nothing. Just half Li square. Substitute the time 5 seconds. You will get it. Another method. Alternatively, we can obtain the energy stored in by writing energy is equal to half Li square at 5. Means at the time period 5. That is uh, half Li square. Half L minus half Li at 0 seconds and 5 seconds. So what is this will go 0 and only half Li square will be there. Half L is 5. I is how much? I 2 t power 3. So 2 into 5 power 3 whole square. So 2 2s are 4, 5 power 6 will be there. So 4 into 5, 20, 20 divided by 2. So like this, if you find 156 kilojoules will come. If you substitute here everything, you will get 156. Same value will come. So we have two methods here. Just use half Li square. Okay, next. Inductor, another example we have. Consider the circuit in the figure under DC conditions. Find I VC, that is capacitance voltage, voltage across the capacitor. Now here mixed circuit is there, capacitor is there, inductor is there, resistance also there. So what we need? Voltage across the capacitor, and we need the complete total current, and we need the inductance current. So through the inductor, what is the current? Next, and the energy is stored in capacitor and inductor. So see the circuit. So we have three resistance and one capacitor and one inductor. Okay, and voltage is given. What voltage is given here? DC. When voltage is DC, what happens to the capacitance? It will act as a open circuit. What happens to the inductance? It will act as a short circuit. So rearrange the circuit. Okay, okay. We can rearrange the circuit, but that is okay. We can rearrange the circuit, then we can find what is I. So when you rearrange the circuit, the capacitance will become open circuit and the inductance will become short circuit. Now, because this is open circuit here, this resistance effect will be zero because there is no current flowing in the resistance. So zero, no effect in that. So only these two resistors are in series, and the current is nothing but 12 divided by total resistance. 5 plus 1, 6. 12 divided by 5 plus 1. And that current also known as inductive resistance also, IL. Because it is flowing through completely inductance. IL is equal to 12 divided by 6. And 2 amperes it is. So that is the I we got. That's as per the question. We need IL. We got IL. That is nothing but 2 amperes. Next we need VC and I. Total current also we need. Total current also we got. That is 2 amperes. Two answers we got. I and IL we got it. So we need VC and energy stored. Okay. Next step. See, the voltage VC is the same voltage. What is the voltage across this capacitor is nothing but the resistance effect is gone. So the voltage across this VC is nothing but here. The same voltage, what it is across the resistor. Means the resistor, what the voltage is developing, that dissipating or using, that is nothing but same voltage. So what is the voltage across the resistor is nothing but 5 times I. So what is I? Already we know 2 amperes. 5 into I. So 5 into 2, 10 volts. So we got VC also. VC is now 10 volts. Because it's an open circuit, the voltage will be there. Okay, it will not store anything, but the voltage across the capacitance will be there. Okay. The energy in the capacitor is half CV square, CVC square, the voltage across the capacitor square. Then substitute this half, C is nothing but 1, how much it is? 1 farad. Okay, 1 farad. Generally it won't be there, but for example it is given. Half 1 farad times VC square. What is VC? That is 10. So 10 power 2. 100 divided by 2, 50 joules. Same inductance. Inductance is half Li square. So half L is nothing but how much? 2 henries. That is 1 Henry. 1 it will become I square. What is I? 2. 2 power 2, 4. 4 into 1, 4 joules. So WL inductance energy is nothing but half Li square. That is IL square. Half inductance is 2 and current is 2 whole square. That is 4 times 2 by 2, 4 joules. So like this we have to find the inductance and capacitance energy stored. Now, last topic, series and parallel combination of inductance and inductance. So, we aim to replace series parallel connections of inductor by a single equivalent inductor, same like a resistor. So, inductance and resistance, same calculation. Capacitance is the opposite to the resistance or the inductance in series parallel. See here. When it is connected, L1, L2, L3, L up to Ln inductances are connected in series, then it can be redrawn by its equivalent circuit, L equivalent, like this. L equivalent. We can redraw the circuit all together and we can write as L equivalent. Now we know, we have to know what is L equivalent. L equivalent is nothing but it is inductors in series combined same manner as resistor. So all are together. The equivalent inductance of a series connected inductors is sum of individual inductances, L1 plus L2 plus L3 plus up to Ln. So like same like a resistor. So L equivalent is nothing but L1 to L2, L3, Ln. So don't need to confusion. You can just remember what is resistance properties and its a series parallel combination properties. Same inductance is there. Next, parallel. Parallel, same like resistance. 1 by L1, 1 by L2, N by L3 like this, and you have to again reciprocal. So we now obtain n inductors connected in parallel by comparing the circuit. L1, L2, L3, L4 are connected in parallel. Then we can write as a L equivalent. What is the L equivalent? So note that inductor in parallel combine in the same manner of the resistors in parallel. The equivalent inductance of parallel inductor is the reciprocal of the reciprocal means opposite of the reciprocal of the sum of the reciprocal of the is the sum of the reciprocal of the individual inductances. Here the wording you have to understand. Same like resistance only, but again I am repeating that same here. Parallel inductors. Parallel inductors is the reciprocal of the sum. Means once you get the total, you have to make x. Means opposite. Means reciprocal you have to do. After taking the total. What is total? Is nothing but sum of the reciprocal inductance. Means each inductance you have to first make opposite. That is make reverse 1 by L1 plus 1 by L2 plus n by L3. Take all 1 by Ln. Together means all sum. Again make reciprocal. 2 times you have to make reciprocal. First individual reciprocal, then sum. Like a series resistance, like a series inductance. Sum it again. Again reciprocal. Again make it opposite. Then it will give the resultant. See here, 1 by L equivalent. This is 1 by L equivalent. As per this explanation, only half we are telling here. Only half. That is 1 by L equivalent we are telling, not L equivalent. L equivalent is nothing but 1 by L equivalent. So 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by L3 up to 1 by Ln. Now what is L equivalent? Opposite that one. Make it a reciprocal, you will get L equivalent. Okay, now we have only two, let us check. Remove all this. Remove all this. If we have only two, then what happens? It will become L1 plus L2 divided by L1 L2. But it is 1 by L equivalent. But I want L equivalent. So L equivalent means again reverse. So L equivalent will be L1 L2 multiplication will go on the top. L1 plus L2 go come under the division. So it will become L1 L2 divided by L1 plus L2 L equivalent. So like this we have to same like resistance, no change. So we have another example. Find the equivalent inductance of the circuit in the shown. Okay, we have how many inductances in say we are asking the equivalent from the left side. So where we have to start? From the right side. If it is asking the inductance or resistance or capacitance on the right side, then where we have to start? From the left side. So be careful this one. So we need it here on the left side. So we have to start from the right side. So these three inductances are in series. How much it will be? Please plus it. 20 plus 12 plus 10. 2, 3, 4. 42 Henries is the series. 42 Henries is the equivalent. Now 7 Henries and this one 42 Henries will become parallel. Same like resistance. Make the parallel, that is 7 multiplied by 42 divided by 7 plus 42. We will get some value. 6 Henries. 6 Henries you will get. Now once you get here 6 Henries of these complete equivalents, this complete series and parallel equivalents, we got 6 Henries. Then this 4 and 6 and 8 in series. So 6 plus 4, 10 plus 8, 18 is your equivalent. 18 is your equivalent inductance. So one example, I think we have last example. Okay. Okay, in the for the circuit is shown, current is given 4 to minus e power minus 10t milliamperes. For I2 of 0 means initial condition is given here. I2 at the 0 means the time is 0 minus 1 milliampere. Now find I1 at 0 condition and V of t, V1 of t and V2 of t and I1 of t and I2 of t. All things we have to find. Okay, now this is a circuit. It is a circuit, inductance, three inductances are there. We need many items. I1 of 0 we need, V of t, V1 of t, V2 of t, I1 of t and I2 of t. What is the I1, I2? Is nothing but your I1, I2 is the 4, I1 is in 4 Henry's inductance, I2 is in 12 Henry's inductance, I is in 2 Henry's inductance. V1 is in this one, V2 is in both same because voltage in parallel circuit is same. So V2 is same in 4 and 12 Henries. Only I will change. So just find from I of t, 4 of 2 minus e power minus 20 milliamperes, I of 0, just substitute I of 0 in this. So substitute 0 in this. In this equation, substitute 0 wherever t is there. So 4 of 2 minus e power of 0, 10 times 0, e power of 0. E power of 0 is 1. So it is 4 times 2 minus 1, that is 4 milliamps. So at first answer is we got it. I of 0 we got it. I of 0 is nothing but 4 milliamperes. Means total current. Total current is nothing but 4 milliampere. Now if you know the total current here, what is the voltage? Multiply these two, you will get it. So since I is equal to, what is I? Is nothing but I1 plus I2. But we need, let's take I1 plus I2. We know I2. I2 of 0 we know minus 1 milliamperes. Then what is I1? So I1 is nothing but I minus I2. I minus I2. That is I of 0 minus I2 of 0. I of 0 we got it. How much? 4 milliamperes. Now I2 of 0 already given minus 1 milliampere. 4 minus of minus plus. So 5 milliamperes. So at the initial condition, at time 0 the condition. What is the total current? I 4 milliamperes. And what is the current I1? 5 milliamperes. And what is the current I2? It is minus 1 milliampere. Means reversely it is going. Means it is discharging. Okay, next. The equivalent inductance. Find the equivalent inductance so that we can know what is the voltage. So equivalent inductance, these two are in parallel. 4 and 12 are parallel and 2 is in series. So 2 plus 4 and 12 are in parallel. 4 and 12 parallel, 3. So 3 plus 2, 5 Henries. Total inductance is, equivalent inductance is 5 Henries. Now we can know what is voltage. So V of t is nothing but L equivalent di by dt. Total current differentiation L equivalent. L equivalent is nothing but already we find 5 Henries. And di by dt. What is di by dt? I is nothing but 4 times 2 minus e power minus 10t. Take out this 4 and if you integrate this 2, it will become 0. So we have to integrate only this one. So minus of e power minus 10t. So minus 1 well di by dt. Yeah. Why minus 1 is coming? Yeah, minus 1 because minus 10. Minus 10 and this is the minus 1 and e power of minus 10t. Okay. L di by dt 4. Yeah, minus this one. This minus is coming out, that is minus 1. And minus 10t, e power of minus 10t, if you differentiate, minus 10t will come out, that is minus 10 come out, this is again minus 10. E power of 10 minus 10t, differentiation differentiation is e only. So minus of minus, it will become plus 5 for the 20 and 10, 200 e power of minus 20 millivolts. Okay, next we got V of t 200 e power minus 20 millivolts. Now what is V1? We have to know what is V1. V1 is nothing but 2 di by dt because current is flowing I. So differentiate I, what is I, then you will get V1. So 2 di by dt, 2 into minus 4, if you differentiate, same equation will come. 2 di by dt, minus 4 and minus 10 e power 10t, you will get 80 e power of minus 10t. So like this, you will get the V1. Now next, V2. Since V is equal to V1 plus V2, like this also we can go. We know that what is V is nothing but V1 plus V2. So we want V2 is nothing but V minus V1. So V of t minus V1 of t. V of t is nothing but 200 and this is 80. 200 minus 80, 120. 120 e power of 10 minus 10t. So we got all voltages V1, V2 and V. Now what we need? I1, I2 we need. Okay, at t, not at 0. 0 we got it. I of 0 we got, I1 of 0 we got, I2 of 0 we got. So I1 of t is nothing but integrate. Integrate this 1 by L dV by 1 by L dV integration. So 1 by L is nothing but 1 by 4 and integrate from 0 to t V2 of t plus I1 of 0. Now substitute because V2 and V1 both are same here. So V2 of t, I1 of t is nothing but. Now substitute 120 by t because V2 we got it already. V2, what is V2? 120. So 120 by 4 e power of minus 20 we have to integrate. So then what we will get? An initial condition we know 5 milliamperes. So substitute this, then you will get 8 minus 3 e power of minus 20 you will get it. Same. I2 of t is nothing but 1 by L, that is 12 henries, V2 of dt. Okay, now I have 0, then substitute, we will get it minus e power minus 20. Because why it is minus? See here, first one is I1 is nothing but your 8 minus 3 e power minus 20, but I2 is nothing but minus e power minus 20, I2, because it is discharging. Okay, so like this we have to find the values. Summary: the current through the capacitance is directly proportional to the time rate of change of voltage across it. We know I equal to C dV by dt. Now current through the capacitor is 0 unless the voltage is changing. Abruptly it cannot change. Thus a capacitor acts like a open circuit to the DC source. The voltage across the capacitor is directly proportional to the time integral of the current. The voltage, if you want, take the C this side, 1 by C integral of I dt. Okay, that is given by like this with initial condition. Now next, capacitor in series and in parallel are combined in the same way as conductance, opposite to the inductance. Like in now inductance, the voltage across an inductor is directly proportional to the time rate of change of the current through it, L di by dt. Now the voltage across the inductor is 0 unless the current is changing. Thus the inductor acts like a short circuit because current if it's changing only, then it will store the energy. If it is the DC current, it will act as a short circuit. The current through the inductor is directly proportional to the time integral of the voltage. So we need I, then just integrate the V. So I is nothing but integration the V, 1 by L integration the V dt with initial condition of I. Inductors in series and parallel are combined in the same way as resistors in series and parallel. So like this we have finished the chapter 5 and we have some table, we can go through it. What is the relationship and what is, when resistor is there, what is the equation, Ohm's law, and what is the capacitor and what is the inductor. Voltage to current and current to voltage, what is the equation. Now power. Power is half I square R or V square by R, and energy here half CV square, energy here half Li square, because we don't need power in the inductor sign capacitor. We need main energy, how much it is stored. But in the resistor, we need power, how much is wasted. That's we not, we need it. So series and parallel all there here. For DC circuit, resistor act as same. I know it will act as a capacitor open circuit and inductance as a short circuit. Circuit variable that cannot be changed abruptly, which cannot be changed abruptly in resistor, no, not applicable. Voltage cannot be changed abruptly in capacitance. Current cannot be changed abruptly in inductance. Okay, so some problems are there. You can practice, but in the final exam and mid exam, I am not asking from this. If you want the full knowledge, you can practice the problems.